Hello, welcome. Did you know that you can use a matrix to solve any linear system? Yeah, it's pretty amazing. And that's what we're going to do in this video. We're going to take this linear system and use Gauss-Jordan elimination to find the values of x, y, and z. And it works for everything, right? Any linear system. So thanks Gauss and thanks Jordan for this algorithm. How does it basically work? Well, in this case, we take our linear system, and I'm going to circle that right here. And row by row, we take our coefficients of x, y, and z and plug them into our matrix, our augmented matrix. And then you'll notice this line in the augmented matrix right here. That separates the coefficients of the variables on one side and the constants on the other. So let's take a look at that. In the first row, we have 1x, negative 2y, and 3z. And here are those coefficients. Then we have 1, 2, negative 1. Here they are. And then 3, 2, negative 5 right here. And then we have our constants 1, 13, and 3. Now that in itself is just rearranging the information. But the elimination technique we're about to look at takes the augmented matrix and manipulates it so we can clearly see the values of x, y, and z. And that's exactly what we have down here. This is called a matrix in reduced row echelon form. Echelon is the order. It's reduced because we can see now the values of x, y, and z. I also want to point out that it is commonly referred to as RREF. Why is this so amazing? Well, it works for everything, so that's a really satisfying thought. But also, we can tell what the values of x, y, and z are. Let me just circle that again. Okay, so for example, we have the coefficients of x are always in the first column. So that tells me 1x equals 3. So it solves for x. X equals 3. The second row, we have 1y equals 7. So it tells me that y is 7. And finally, 1z is 4. So this matrix solves for x, y, and z. So to get in this form, notice something. Notice that we have this diagonal of 1s. This will always happen as long as there are 1s to be had. There could be all 0s in a row. We just put those at the bottom. You'll see that in other videos. These are called leading 1s. And then they're the first, essentially the only number in the row that's not 0. That's what a leading 1 is. Elsewhere, we have 0s. So that's the goal. So I want to visualize getting there. How do I get there? There are 3 basic operations we can use that won't change the solutions to the variables, but will enable us to get to reduced row echelon form. So the first thing we can always do is swap 2 rows, and this is my notation for that. You'll see me write out swapping rows. We can always scale a row or multiply it by a number, so k times some row. And finally, this one is like elimination, essentially, if you've solved for variables and systems of equations. In a system of equations, you can add one row to another to cancel out variables. That's essentially what this is. You add a multiple of one row to a multiple of another row, you would get it 0. And then put that new equation into some spot in the matrix. I said the jth row, but it could be the I or jth row. So that one's the trickiest one, but it's essentially what we do with elimination in linear systems. So let's try this out. So I'm gonna remind you of this at the end of the video and give you a little template. But the first thing we want to do is set up the matrix itself, so the augmented matrix. So row by row, 1, negative 2, and 3. You can do this with me. 1, 2, negative 1, 3, 2, negative 5. Constants on the other side, 1, 13, and 3. Okay. The first thing we're always going to do, and again, I'll remind you of this kind of roadmap at the end, is get a 1 here, our first leading 1. But we have a 1 there, done. Second thing we want to do is get 0s below that. So in these 2 spots here. It'll always be that if you're using this algorithm. So how do we do that? Well, if we just take row 1, I'll say this, I usually write everything in addition. So if I take the opposite of row 1, and add it to row 2, that'll cancel out and get me a 0. I'll put that result, in the second row. And I'm using this one right here. Then I want to do negative 3 times the first row, add it to the third row, and put it in the third row. So let's look at that and see why this works. So I'm going to keep rewriting the matrix, and these little notes tell me what I have done to get to the next matrix. So we haven't done anything to the first row, so I'm just going to rewrite that. So no computations needed right there. But then what are we doing? Well, we're taking, as this command says right here, I'll just kind of highlight that. As that command says, we take the opposite of the first row and add it to the second. That's going to get us exactly what we need, because -1 plus 1 gets me 0. We're going to put that result in the second row. So 0. Then -2 times -1 is 2, plus 2 is 4. Then -3 plus -1 is going to be -4. And then finally, -1 plus 13 is going to be 12. Okay, now we follow this command here. We do -3 times the first row plus the last row. So let's do that. So -3 plus 3 is 0. So that's our goal, is to get those zeros everywhere else. We got the first one. So here, first column of zeros below that 1. Then we have -2 times -3, which is 6, plus 2, which is 8. Got that. And then 3 times -3 is -9, plus -1 is -10. Right? -9 plus -5, which is -14. And then -3 plus 3, which is 0. Okay, so always first we want to get a 1 in this spot and then 2 zeros beneath. Next thing we want to do is get the 1 in this spot. So let's do that next. So I'm going to do 1/4 times that row, and that is scaling a row. So 1/4 times the second row. Okay, so in this is a really nice one because I'm not doing anything to the first or third row, so I'm just going to rewrite those things. 1, -2, 3, and 1, and then 0, 8, -14, 0. And then I just take 1/4 of every value in the second row. Okay, we're almost done. Okay, scroll down a little bit. I'm going to definitely need more room for this. Okay, so let's just backtrack. We got a 1 in this spot, 0's below it. We got a 1 in this spot here as well. The next thing I'm going to try to do is get a 0 in this spot. That's the next thing. So 1 and then 0's below it. 1, 0's below it, and so on and so forth. So in this case, how am I going to do that? Well, I'm going to take -8 times the second row, because we have a 1, it's just going to be the opposite of 8. So -8 times row 2, add it to row 3, and put the result in row 3. And that again is this step right here. So in this step, we're just going to rewrite the first and second rows and do some computations in the third row. Notice what's happening now. This 0 right here times anything is 0. So it's not going to change the 0 we already found. It's not going to force us to go back. So that's still a 0 in this spot. But now we have -8 plus 8. We get the 0 in this spot. Finally, we have -1 times -8, which is 8. And then 8 minus 14 is -6. So we get our -6 in this spot. And then here we have -24 plus 0 is -24. So to recap, we got our 1, the 0 is below it. We got our 1, 0 is below it. And as you might not be surprised by, we now get another leading 1. So we're getting this diagonal of 1s and 0s below it first. So to get 1 now in the third column, we do -1/6. Sorry. Oh boy. Here, scrolling down. Okay, sorry about that. So we're going to do -1/6 times row 3. And again, we're not doing anything to the first or second row. So 1, -2, 1, -2, 3, 1. I'm not changing that row. 0, 1, -1, 3. Not changing that row. 0, 0. -6 times -1/6 is 1, which is what we wanted to get. And then -1/6 of 24. -24, excuse me, is 4. And we're almost finished. What have we done so far? We start with a 1 in this spot, we got 0's below it. A 1 in this spot, we got 0's below it. We got a 1 in this spot. There's nothing below it, so now we start going up. We want to get zeros above in these two spots. Very similar to what we did before. We're going to do row 3 is already the opposite of row 2. It'll get us a 0 plus row 2, and put the result in row 2. And then we have a 3 up top, so we have to do -3 times row 3. Well, we don't have to do that, but I think it's the easiest way. Plus row 1, and put the result in row 1. Okay, let's write this out. In this case, I'm going to write the last row first because that's the one we're not changing. That's essentially finished because we have a 1 and everything else is not 0 in that row. So above it, what's going to happen? Well, these zeros are not going to change anything above it. That's why they're there. That's the strategy. So we still have 0, 1. The only computation is to do 1 plus -1 for the coefficients. We get 0. And then 4 plus 3, which is 7. And then in the first row, this 1 is not changed because, again, we have -3 times row 3 plus row 1. We're now looking at this command. We just did the second one, but now we're doing this one. We're doing -3 times the third row and adding to the first row, but the zeros don't change anything. So we're still going to have 1 and -2. Finally, we get this 1 times -3 plus 3, which is the 0 we need. And then we have 4 times -3, -12. Plus 1 is -11, right? And we're almost finished. So to recap, again, we got the leading 1, 0 is below it. Leading 1, 0 is below it. Leading 1, nothing below it, went up. The only thing left now is to deal with this -2. How are we going to do that? We're going to take twice row 2 and add it to row 1, and then put that new equation to row 1. And again, all we're doing is elimination, taking the result and putting it into a spot in the matrix that works for us. So in this case, no computations for the second or third rows. So we have 0, 0, 1, 4, 0, 1, 0, 7, and these two numbers are not going to change, 1 and -2, because, no, wait, the 1 is not going to change, excuse me, because of the 0 in this spot. But this 1 will affect the -2 above it. When we do -2 times 1, we get when we do 2 times 1, that's 2, plus -2 is the 0 we need, and these zeros, nothing's changed. Finally, we have 7 times 2, which is 14, 14 minus 11, which is 3, and we're finished. We now know that x is 3, y is 7. Again, x is 3, y is 7, and z is 4. So that's our solution. Now, I want to point out a few things to you before you go. Thanks for hanging in there. I know this is a long video. The first thing to point out is that, scrolling up, where is it? I think in this spot right here. Let me highlight this, kind of a mess. So we have reduced row echelon form, which is what we obtained. I'm going to compare them side by side. So down here in the bottom, this is the reduced row echelon form. It's just leading 1s and 0s everywhere else. Any row of 0s goes at the bottom. But not reduced row echelon form. So this is RREF. I'll write this down. If I just said row echelon form, this is also really useful because what this does is it tells you the value of z, right? Z is 4. I'm going to write this over here. Z is 4. And then you could say in the second row that that's y minus z equals 3, right? And if you know z is 4, then that means that y minus 4 equals 3 and y equals 7, which is what we were doing in the matrix. And if you know z and y, you can figure out x in the same way, right? X minus 2y, or minus 14 because y is 7, plus 3z, or 3 times 4 is 12, equals 1. So what does x equal? Well, this is x minus 2 equals 1, so x is 3. So this, I mean, if you get to reduced echelon form right here, not row reduced echelon form, you can quickly still solve for the values of your variables, usually because you just take the last row right here and take that variable and plug it back into the previous ones. So the difference here is that in row echelon form, you don't have zeros everywhere else, but you have your diagonal. It's kind of a mess, sorry. I'll rewrite it over here. In row echelon form, what you essentially have is a diagonal of 1s, and anything before those ones is a 0. In the other spots, sorry, scrolling, jumping around there, we have other values. It could be any numbers there, and then I'll say D, E, and F here. So this is kind of what it looks like. You have this diagonal still of leading ones and zeros in front of them here, so that you can solve for the last variable and plug it back in to find the others. That's row echelon form. And again, and you'll see this in the next video, or if you want to watch it, or in general, lots of things can happen in these matrices. But the general strategy is to start to get a 1 in this spot. Let me change colors. I'm going to write down the whole algorithm. I'll zoom in a little bit here. Moving over. Okay. It's really important that you have some kind of visual strategy. It makes this whole process, at least for me, very quick. We start with a leading 1, and then we get zeros below it. I think it's snapping to the tool. Oh boy, it's really confused, sorry. Then we get this leading 1 and get zeros below it. Then we get this leading 1, there's nothing below it, and we go up. And then finally, fix that arrow, we get this 0 here. So if you want to write this down as a template, let me just make a new image. So 1, 0, 0, 0, 1, 0. I'm going columns now, 0, 0, 1. And then some numbers, let's say A, B, and C. This is what RREF looks like. And to get here, let's just write those steps down. This is my first step. My second step is to get zeros below it. My third step is to get this leading 1 and then zeros below it. Let me actually color code that nicer. This is 3. And then 4. Get zeros below it. Finally, we get our last 0 in there. That's step 5. And then we want to get the zeros above it. That's step 6. And then finally step 7. But I don't like that color coding in there. So 6, sorry. And then let's do, yeah, I guess I'll just do red. So 7. And this is what I love. I love that these 7 steps solve all linear systems of 3 variables. And then you might find that there are more efficient ways to do particular matrices, but I love that this solves any 3 by 3 matrix. If it's larger, if there's more variables, it's just more steps, but still you're looking for the leading 1, zeros below it until you can't go any further, and then you start working your way up. All right, I hope this helped.